Thanks a lot for joining us today. My name's Joseph Artuso. I'm the Chief Commercial Officer at OpenBCI. I've also got Phil and Musa with me today, and we're going to show you some of the latest developments that we've been working on internally with Galea. If you're OpenBCI is going to be at a couple conferences coming up in the near future. We're going to be at ITSEC in Orlando at the end of November, and we'll be at CES in January. So if you're at those events, let us know, give us a heads up. You can always reach out to us via galea@openbci.com. If you have questions about today's webinar, you can also reach us that way. Couple things to take care of in the chat. Let me remind everybody that we've got this Q&A function built into Zoom. You can ask questions, via the Q&A function in Zoom. And then once someone's asked, you should be able to, thumbs up or upvote other questions that you want answered. We'll try and work in answers to the most popular questions throughout the webinar. Sometimes we may pause if it's relevant for the stuff being shown at the moment, or we may hold a bunch of them till the end. But can somebody out there maybe just submit a test question or two to make sure that it's working? There we go. There are some test questions. Thank you, thank you, thank you. All right, that's good. I can see we have a good audience today. Andrew Sci-Fi, if you're asking questions in the chat, they're not going to get answered. You've got to use the Q&A app. It's another one of the little buttons in Zoom. All right. So then, without further ado, this is kind of the fourth webinar in a series of webinars that we've done about Galea. We wanted to use these as an opportunity to kind of share the latest developments. So I'm going to let Phil and Musa maybe get started, explain what's on the menu for us today, and then, we'll take it from there.
All right. Well, thanks, Joe. What we're going to show you today is some new demo that we've built here in OpenBCI in-house. And this demo is showing off a couple of new features that we built into the Galea headset. So let me first explain what I've been playing here. Over in the top right, or the top left, you can see that there is a little pipe network that I've been building out. And this pipe network has liquid that's flowing through the different pipes. And so what my objective is in this game is to build a grid or a network of pipes from the left corner down to this right corner down here. Now, you may have seen me look back and forth at the different conveyors here. Now, these conveyors have the parts that I need in order to build this network. But you'll notice if I start that the pipes are moving really quickly on these conveyors. They're moving so quickly that I can't really interact with them. And so what I need to do is use both of my hands and slow down the conveyors so that I can interact with them. In order to interact with these different parts, I'll look at them using the eye tracking that's in Galea. And that'll cause the piece to appear right in front of me. I'll show that one more time. So here's the piece right in front of me. Now here, I need to rotate this piece so that it will fit into my network. So I'm going to grab a better piece that I like a little more. This is a good one. And here I actually like this. So I'm going to go ahead and place it using an eyebrow movement. So we have these new buttons that we've kind of added. They're kind of like face buttons. That's a good way of thinking about them. They're new inputs that we can add beyond just what you can do with your traditional VR controllers. And so in addition to using eyebrow movements, I can also use cheek gestures, right cheek and left cheek, just movements, in order to rotate the pipe in a direction that I want. So there are a couple of different kind of inputs that we can use in order to make this a little bit more interactive. So I'm going to play this for a little while just to give you guys an idea. I'm going to actually restart real fast and give you guys an idea of how all of this works.
Musa, could you try maybe just refreshing the screen share quick? Because it does, the video comes through really Zoom plus VR view sharing. There seems to be some video throttling that Zoom does to the screen share. Doing our best. It seems to work best when we right after starting, the screen share. So we may start and stop the VR view share just to make it as good as possible. But we're gonna look into better ways to share the VR views in the future. But yeah, it's coming through a little clearer now. Go ahead.
Okay, so I'm going to play through this a little bit, and maybe you can describe, Musa, what I'm doing here.
Yeah, sure thing. So he's going to restart again. So this is a game, as he mentioned, is built entirely in-house, and it demonstrates some of the functionality of the Galea headset. So the purpose of this demo, as he mentioned, is to connect the pipes from the top left to the bottom right. So complete the pipe network before the liquid flows out of the pipe and causes you to fail the level. And as he does this, he needs to his hands are very busy. He's using his hands to control this conveyor belt of pipe components. And when he finds a component that he likes, he has to slow down the conveyor belt and has to rotate it in place. So because his hands are busy, he needs to be able to somehow manipulate the pipe elements. So that's why we decided to use this sort of face gesture classifier in order to provide additional functionality. And there's many different uses for this. So if you can think, for example, of a pilot or a race car driver, their hands are very busy controlling their vehicle, but they may need to do other things. And Phil can get into more detail about different applications of this type of system. And so as he's working on this, he's both using his hands and he's using his eyes. So the eye tracking is used to look at which component he wants to use, and that allows him to select the component. And then he's using these face gestures, which we will describe in detail later, like using his movement of his cheeks and his eyebrows in order to manipulate and place these components. So I'll just let him try and fill out more of the thing, and hopefully he can outrun the goo that's flowing through the pipe.
All right, here, maybe I can get one.
You're getting close to the.
Oh, man. All right, next time.
Well, it was a good run.
All right.
Yeah, he's made it further than that before.
All right. So Musa, maybe we can talk a little bit about how we went about creating this application and what some of the stuff under the hood looks like that enabled us to kind of make this kind of new sort of interaction system for VR. And so I'm going to walk over here. Over on this portion of the VR space here, we have what may look very familiar to people who have used the Open DCI GUI before. We've actually gotten a lot of really good feedback from our early partners who have said, you know, it's great that we have the Open DCI GUI, but it's difficult for us to switch between both the GUI application and the VR application, because when we do that, sometimes it requires either having two people, or we have to take off the headset and then put it back on when we want to go into VR. But obviously, if you take off the headset, you can't really check all of your signals using the Open DCI GUI because you're gonna move the headset again. And so what we've done is ported a lot of what you can visualize in the Open DCI GUI, and we've added it here so you can place this in VR wherever is convenient for you. And you can move this wherever you need to. You can attach it to your wrist or whatever you want to do. Make it as a HUD. It's a pretty movable component. And we've made this prefab in our Unity SDK, so it's really easy for developers who either want to create a new project or update an existing project to add in these features. So over here on the right, we have a whole bunch of raw data. Can you walk us through what all of this is doing, Musa?
Sure thing, Phil. So as you were mentioning, we're using electromyography or EMG in order to manipulate those pipe parts in order to place it in the game. So the top 4 channels that we see here on the right, if you can gesture to them, are the electromyography. So we have electrodes placed above both of the eyebrows and below each of the cheeks. And that measures electrical fluctuations in so whenever you activate the muscles. And the advantage to using EMG over something like a camera is, first of all, the VR obscures the view of your face because of the headset. And the second advantage is that it even picks up isometric muscle contractions that will not show up as movement on camera. So anyone who's ever lifted weights knows that you can exert a significant amount of muscle activity without actually moving a weight. And that is all picked up through electrical activity. So below the 4 EMG channels, we have vertical and horizontal EOG. So EOG stands for electrooculogram, and it measures the movement of the eye, and the eye can be visualized as a dipole. So when the eye moves, there are large fluctuations in the vertical and horizontal directions, and that can provide us with information like saccades. And that gives us a quantifiable metric along with what we already get from the Vario eye tracker, which gives you a direction vector and a movement vector. So below EOG, we have passive and active EEG. EEG stands for electroencephalogram. And those of you who are familiar with OpenBCI knows that OpenBCI has a lot of experience with electroencephalography. So we have a lot of existing products that acquire EEG data. The top two are passive EEGs, and they're at the FP1 and FP2 locations. That's on the frontal lobe. So the frontal lobe, as you know, is the frontal lobe of the brain is what regulates executive function, like planning and thoughts. And so the reason that is using passive electrodes is because it's on a bare skin region. There's no hair in that region. And if you've worked with EEG before, you know that getting data from hairy skin regions is quite difficult because you need to get good electrode contact and you need to minimize skin electrode impedances. So for the hairy regions, which are listed below the passive EEG, we have the active EEG, which is we have 8 active EEG channels, which is dispersed along the crown of the scalp all the way back to the occipital lobe, and it covers all the major EEG regions like the temporal lobe, the parietal lobe, and the occipital lobe, all of which govern different mental activities. So, for example, the parietal lobe is used in motor planning and motor execution. The temporal lobe is for memory and decoding audio speech. And of course, the occipital lobe is where your visual cortex is, so it's involved in all the visual processing. So below all of this, your primary biometric data, we also have our auxiliary biometrics. The first of which is electrodermal activity, also known as EDA, which measures galvanic skin response. So this is useful for deriving metrics such as cognitive load and mental stress. And this is highly useful because your body responds to these stressors and cognitive loads physiologically. So whenever you're excited or you're stressed, your body will respond by opening up your sweat pores a very small amount. So you can realize this, like if you're standing on the edge of a bridge and you're afraid of heights, for example, this will you'll have a very clear electrodermal response to this because your skin conductance will increase as your sweat pores open. So that is a very useful metric, and combined with the other metrics, we use sort of a sensor fusion in order to gather these important cognitive scenarios where your subject is either stressed or they're under some sort of cognitive load. So below electrodermal activity, we have photoplethysmography, which is where we shine two lights, two LEDs in the red and IR spectrum at the skin. And as fresh blood is pumped through your veins, you see these peaks in the PPG signal. And if you can detect these peaks, you can easily gather the heart rate. So the challenge is like, can we consistently measure these peaks? And that will give us the heart rate, as you can see on the top left. And as you can see, his heart rate is steady at around 70 hertz. And then the ratio between the reflectance of red and IR light also provides us with oxygen saturation. And that is because the way oxygen binds to hemoglobin affects its color reflectance. And that way, if he holds his breath, which he's doing right now, you can see a small decline in oxygen level. It's going to go from saturated, which is 100%, down to around 80 and then 70% the longer he holds his breath, because the blood will lose oxygenation as your body consumes oxygen, and then he's not replacing it because he's holding his breath. So you should see a decline in both his heart rate and his oxygen level as he holds his breath. I'll just let him keep holding his breath until he can no longer hold his breath, and then you should see both the heart rate and the oxygen level recover. As you can see it declining very slightly.
It's a couple seconds behind for us just because of the, you may need to.
Let me restart
it off.
Really quickly. I want to point out, this is a Zoom issue where it'll start off smoothly and then the frame rate will drop after a while. I don't know what causes the issue, but it looks a lot better now. So yeah, you can see the heart rate and oxygen level went back up. And then Phil, I think you can continue talking about the secondary. Well, sorry, the metrics.
So yeah, it was kind of interesting here. I don't know if you saw that before the Zoom call. Kind of, we had to reset the Zoom call, but you could see my heart rate going down as I was holding my breath there pretty clearly. The oxygen level, I don't know if you guys can see that in Zoom, but it was also, I noticed that going down a little bit too. It's it's interesting how these raw metrics can be used to figure out this kind of higher level information. And that's really kind of where we're focusing our efforts now. Is we've got a lot of this raw data point type of information, these time series types of graphs. And now we're starting to look at, okay, how do we use all of this information and fuse it together in order to get kind of these first derivative metrics. And I would call first derivative metrics things like heart rate, things like oxygen level, things like average band powers, which we'll talk about just in a second. And they're things that can basically be derived from the raw data. Now, these first derivative metrics can also be used with each other and with other raw data signals to create what are sort of like second derivative metrics, or things that are even higher levels of information. Musa mentioned a couple already. One is stress and one is cognitive load. And stress is a great example here, because you can think of if you're, on a high peak or on a tall building or something, and if you're afraid of heights, your palms will start sweating. And so you'll see a spike in EDA because your palms will start sweating. You'll also probably feel your heart beating a little bit faster. And we'll notice that here in the heart rate as well, because it'll start to go up a little bit. And then we can use both of those types of informations to start to classify what might look like stress, along with other different parts of information like pupillometry and different parts of the Galea system. And
Phil,
so,
if you can, it's just if you can keep your head, try and keep your keep focused on the graphs. I know you're as you gesture and your head moves, the frame rate kind of is messing with us. But
yeah, sure.
and I think we should try once you get through some of the description of the metrics that you were doing, let's try the breath holding thing one more time on a new screen share.
Yeah, because I think we cut out the demonstration of the breath holding, so we'll do it one more time.
Okay, cool. Let's do a totally fresh start here. Maybe we can do that oxygen saturation thing one more time here.
And while we get that set up, there is one question from the audience that's relevant. It's about the PPG. Do you only get heart rate or also heartbeat events, from the PPG or from the PPG data we collect? And then, that's part one.
Cool. Yeah, I'll definitely take that one. So right now we use heart rate as opposed to heartbeat, but it's an interesting question because we've gotten kind of this request from a number of different people. So it's something we'll look at in the future. And this could kind of look like a unity action or something that fires off on every heartbeat or something along those lines. So it's certainly possible. It's not something we support right now, but definitely something that we could support.
Yeah, and then the other part of the question was just movement artifacts for PPG, but then movement artifacts in general. I can chime in with some answers here, where we're not. Movement artifacts will always remain a challenge with any, kind of wearable biosensor setup. We've applied a lot of what we learned, from building headsets over the last 8 years, trying to take as much weight as possible off of the individual sensors themselves. So we think we've done a pretty good job on that front between pads and springs that we've built into the device and different adjustment mechanisms. The first way you can deal with the motion artifacts is with the mechanical fit of the headset. And then what we're also working on as part of the SDK are some automated data labeling functions where in addition to all the columns of the data that's collected from each sensor, there's kind of marker columns that we can add and dynamic, we want to be automatically labeling questionable data based on motion, where it's like, hey, for these timestamps, it's clear that the head was moving around. We can see all the numbers going off the charts, so that at the very least, if you're not able to reconstitute the data underneath, you can at least identify, okay, these are areas that we might need to exclude from my analysis in the future. But it remains a challenge, for all biosensor systems, for sure.
One of the interesting things we can do, since we're connected to a VR headset, is actually use some of the VR tracking to detect some of those motion artifacts. It's kind of related to what you were saying, Joe, is that, when I was moving my head around a lot, you could tell because the VR tracking is pretty good. And we can, detect that in software and use that as kind of an input to say, hey, there's some motion going on right now. We can look at different types of motion, and that'll give us a little bit more information about what's going on. Cool. So I think, yeah, we got this set up again, and so let's try the oxygen test again. You ready, Musa?
Yeah, so you can start holding your breath now, and then hopefully we can see that reduction in oxygen level. Yeah, so Phil right now is holding a pointer at the tip of the oxygen level. So when his oxygen level is saturated, it's at that point, and we should see it decline to about 80% as he continues to hold his breath. And obviously, you can also see that when you're holding your breath, your heart rate is also suppressed because you don't have as much oxygen. So your body has to like sort of cool down its metabolism because it knows that there's a lack of oxygen supply in the bloodstream. And as he when he finally stops holding his breath, you will see both the oxygen level and the heart rate recover pretty rapidly. So right now his heart rate's sitting at around 50 or 55. All right, so now he stopped holding his breath. So you'll see it go back up. You can see the heart rate going pretty quickly back to 70.
You can see the oxygen level moving too now.
Yeah, it recovered like 5 to 10%.
Cool. So yeah, we've kind of talked a little bit about these derivative metrics up here. Should we talk a little bit about average band powers now, Musa?
Yeah, sure. So as we mentioned before, all the graphs on the right will provide you with raw biometric information, but parsing useful data out of this raw biometrics is quite difficult. And on the left, we've shown you how we've started to create these first level derivative metrics. And one of these metrics is your average band power. So this is where you use a Fourier transform in order to separate out the frequency components of your raw EEG data, and you can put them into bins like delta, theta, alpha, beta, and gamma. So your delta is like your very low frequencies from up to 4 hertz, and your theta is between 4 and 8 hertz, and your alpha is your 8 to 12 hertz, and beta is between 12 and 30, and gamma is 30 and above. And this gives you like some very broad ranges of frequencies where you can sort of judge what kind of mental activity is going on in a broad spatial range. So one that you might be familiar with is alpha rhythms. Alpha rhythms are generated when your mind is relaxed, typically when your eyes are closed. And like Phil can demonstrate that now, like with his eyes closed. And that creates a dominant frequency component in the 8 to 12 hertz range. And for example, the other ranges can be useful in other applications. So like in sleep study, you'll see a lot of very low frequency signals in the 2 to 4 hertz range, and that's encompassed in the delta band. And then when you're drowsy but you're awake in adults, then you see a lot of theta activity, which is between alpha and delta. It's like 4 to 8 hertz. And when it comes to higher frequencies, that's more to do with mental tasks and cognition, such as if you're trying to solve a problem, you'll see more beta information in your signal. And if you're trying to do multiple things at once, like you're both hearing audio cues and you're resolving some problem in using visuospatial computation, you'll see a lot of gamma signals. So right now, Phil's pretty relaxed, so we're seeing a lot of more low frequency alpha type rhythms. And this sort of information can be used in order to eke out useful metrics, such as, like we mentioned in the past, cognitive load and stress. And so we're going to use like a sensor fusion approach where we're using heart rate, we're using oxygen level, we're using EEG, EMG, all of these components, and that should give us a better idea of what's going on with the user.
Musa.
Yeah, oh, go ahead, Joe. Sorry.
Yeah, just one question that's gotten some thumbs up. Do you think that with the data collected, will Galea be able to track anxiety levels, or could the data collected from a system like this be used to track anxiety levels and then incorporate that into like a horror game?
That is very interesting because we've experimented in that vein, trying to elicit mental stress, which is in that same vein of like inducing anxiety. So we've played some games like Half-Life Alyx, which is a very polished game that you can buy right now and use with any VR headset, and it has a lot of very stressful sections in it by its design, where you have to, well, I won't spoil it, but there's a lot of sections which are perfect for inducing mental stress, and that's the kind of experiments we're performing recently. And that will definitely be worked into our stress and anxiety model that we're working on in the future.
Yeah, it's something that, we're selling to, Galea right now. We've got a lot of customers from the gaming sector, and we're excited to see how they're going to be using it, for their own kind of play testing research. But we're excited to see whether there's sort of gameplay elements that they bake in and start exploring. Okay, maybe in future devices, it makes sense to have a small subset of these sensors so that we can roll this out at the actual consumer level. But Galea today is much more targeted as a developer platform, kind of R&D device for people operating at the intersection of head-mounted displays and neurotechnology.
Cool. So Musa talked a little bit before about the different band powers and what these things kind of mean, but it can be a little confusing if you're not like an EEG neuroscientist to kind of go from theta or delta, theta, alpha, beta, gamma to like this is what like restfulness or mindfulness. This is what the brain is thinking, and I think a good way to visualize this is kind of this analogy of going to a closed football stadium. Now, say you're going to this closed football stadium and you've never heard of football before, you've never played football before, you've never actually seen the game, you don't know the rules. But you'd have a bunch of, say, microphones that you can place around the stadium and kind of listen in at different points to hear what's going on inside. And now you might hear things like whistles or cheers, or you might hear like some running or some tackles or something like that. And you might hear them at these different points. And you have to try and make educated guesses about how the game of football is played. What are the rules? What's actually happening? And this is pretty similar to how we can use things like these band powers and these raw signals for EEG to try and listen in at different points on the brain, kind of like the dome in this analogy, and try and make educated guesses about what those different sounds, those different signals mean. And so a couple examples of this are these restfulness and mindfulness classifiers that we built here. Restfulness is kind of related to how relaxed I am. Now, I'm not particularly restful or mindful right now. I'm just kind of neutral. So these are oscillating back and forth. But if I became more restful, this bar would go up. And we do that using some of these average band powers and listening at different places where we have the EEG channels on the Galea headset. Mindfulness works in a similar way. Mindfulness is more related to concentration, the type of concentration that you might think of when you're playing chess, for example, and you're really focused and you want to have like good moves in chess. That's what's related to this mindfulness metric. And so neuroscientists obviously will come up with different metrics that they'll measure using these sensors, and using the other sensors in Galea, you can start to support these different mental states. And that's one of the cool things about this headset. We're not just relying on EEG, but also a whole plethora of sensor modalities. Now, what we showed you in this game earlier was these face gesture classifications, which are another example of some of these first order derivative metrics. Now, do you want to talk a little bit, Musa, about how we got to these face gestures and how we made this happen?
Yeah, of course. So as we mentioned, we wanted to provide as much functionality from these electrodes as possible. So we're using so we're using the EMG in order to add additional functionality to the Galea in combination with all the things that you already get with the VR headset. So
sorry, actually, it's accidentally, sorry.
That's fine. Yeah, so we're using this EMG. I need to pull up the game one more time. 1 second. But the EMG is basically giving you additional functionality. So in this example, we show that he has his hands full trying to control this pipe game. So we are using this biometric data, which tracks the EMG facial muscles in order to control this interface. So he can perform different face gestures, and he can get you can accurately control the interface while his hands are busy. I don't think I'm sharing my screen. 1 second.
No.
Sorry, I forgot to share the screen. There's the game's running in the background. Yeah, sorry about that. So Yeah, so we can demonstrate this this face gesture system. You check the headsets on properly. Yeah. Yeah, so like, can you go ahead and do a left cheek smirk? So there's a lot of different capabilities that you can add. So like these facial muscles that you don't really use for anything in your day-to-day life. I mean, apart from like expressions, we can use to control the interface. So can you do a right cheek smirk? Yeah, thank you. And then do a jaw clench. And do an eyebrow movement. Yeah, can you do a left cheek smirk again? Yes, as you can see, it's highly accurate. So if you use some sort of a naive approach to classifying this type of information, you may fail because of the conventional like feature extraction and classifier method. Like if you're using like a decision tree, for example, it will not generalize well to this type of data, especially with small data sets. So we're recording on like a handful of internal users at the moment. And in order to get good generalization, we have to use advanced machine learning techniques to get this accurate classification. And as you can see from our demonstration, it seems to be working really well.
Let's do a few more of those, Musa. And this time I'll prove I'm not like using my controllers. Like,
yeah, so as he's moving his mouth, it's sort of like jumping between these different features. But like, I'll give him some prompts again, and he will follow through, and you'll see not only the accuracy of the classification, but also the speed of the response.
It's a little tough to read the face gesture text. Yeah.
So can you do a left cheek smirk? There you go. Can you do a right cheek smirk? Do a left one again. Now do a jaw clench. All right, relax. Now do a brow movement. Good. Do a right cheek smirk. Good. Do a jaw clench. Do a brow movement. And now do a left cheek smirk. Yeah, that's good. Yeah, so as you can see, it's very responsive, and he can pretty much do all of these commands on demand as I tell him what to do.
Yeah, so it works pretty well too, just in the game environment too. And you can think of a lot of interesting applications for face gestures like this. Obviously, we showed you an example of using them as like inputs in a game environment. But if we think about VR just kind of in general, VR is really dependent on having a good immersion experience, right? And part of that good immersion and interacting with other people in VR is having good facial gesture recognitions and being able to have natural facial expressions in VR. And so this is kind of what this is going towards, right? If we can classify more beyond just these first few gestures that we've done so far, as we continue to get more and more gestures, we'll be able to create really nice natural interactions in virtual reality, which will really, I think, make multiplayer VR a really interesting experience. Other examples, even outside of the VR space, of something where this could be useful are things like AR performance support for maintenance applications. So you can imagine a maintenance scenario where, say, you're a technician, and in a lot of these scenarios, you have somebody who's actually doing the work and has their hands busy. And then you have someone who's standing right next to them with a clipboard, checking off, like reading to them the instructions, like, hey, do this next, and then checking off that they in fact did that item on the checklist. And so by combining this together in an AR scenario, you can kind of reduce that manpower requirement by half, which is pretty significant when you think about the volume of maintenance applications that need to be done. And so just by using things like face gestures, you can do things like check off those different lists, read through instruction manuals, and there are a whole plethora of interesting applications. I'm honestly really excited to see what people come up with here. So I'm going to exit out of here, and I think what I'd like to do next is maybe Musa, you can walk us through the different sensors on the headset, and then I'll get into how we built some of these different applications and what tools we provide to the software folks who are building their own VR applications and doing it through the Unity SDK that we provide.
Yeah, so as Phil spins up the Unity thing, I will show you guys a sample Galea headset and how it's constructed and where all the sensors are placed. So by the way, you're not sharing your screen, so you just set everything up. Yeah, so here we have I don't know how well you can see this. You see you have the face pad where there's a bunch of electrodes that contact the face. Here we have also our PPG sensor in the middle. So we're gathering, what's it called? Your photoplethysmography data from the forehead. And besides that, we have the electrodermal activity measurement. So the forehead is a perfect location to record this information because we both have a good EDA response and we also have good PPG response there. Then we have our frontal lobe EEG, and below that we have our EMG sensors, which are above the eyebrows. And then we have our vertical and horizontal EOG. And then we have our EMG again below the cheeks. And then if you look at the spine of the device, we have these rubberized electrodes for contacting the scalp through the hair. And these electrodes are placed in a certain orientation, so where you get all the central information, but you also have a lot of occipital lobe information. And yeah, so this is basically an overview of the device. It's not finalized just yet, but this is like a good preview of what's coming. And I think you can take it from here to demonstrate the Unity environment.
Great. Yeah, let me share the screen here. All right.
One question in the chat, and something that comes up every webinar. What's the highest frequency, EEG frequency? Really, let's talk about. Can we talk a little bit about the sampling rate today, and then where we're going with it in the future? And what that means as far as like the EEG frequencies that we can read.
Sure. Do you want to?
Yeah, I can take this one.
Yeah.
So right now, all of the biopotential biometrics are sampled at 250 hertz, and the integrated circuit that we're using can support up to, I think, like well over 1,000 hertz. It can do like 8,000, I think, is the absolute maximum. So, and when it comes to features that you can extract, we have what's called the Nyquist frequency, which is half your sampling rate. So you can reasonably extract features below half your sampling rate. So at 250, you're looking at 125 and below. And if you can sample above 1,000, you'll be looking at 500 and below. And that's the information that you can gather from that. So with EEG, usually you don't need very high frequencies, but for data types like EMG, where you have a lot of very high frequency activity, EMG can support definitely well above 2,000 hertz. You can eke out a lot more information from that. I hope that answers the question.
Yeah, thank you. Yeah, so we're already currently the sampling rate's at 250 hertz, and we're pushing it up to 500 and 1,000 even after that. Cool. So yeah, I think carry on with some of the Unity and even kind of improved connectivity in the GUI stuff that we wanted to cover as well.
Yeah, absolutely. So I think the first thing I'd like to talk about is how we've improved the ability to connect the headset just from the start, from turning it on and getting it connected and streaming data into your device or into your computer. And what we've done is we've listened to a lot of feedback from our early partners, and they've told us it's a little difficult and complicated to connect in the old method that we were using. Before, we had to start up a Windows hotspot, and then you had to change some settings, and then the headset would connect to the Windows network, or the network that Windows or Linux or whatever operating system you're using started up. We've changed that now. We've made it a lot more streamlined. So now we have what's called an access point on the headset itself. And so the microcontroller that's on the headset will start up its own network, and then you in your operating system can connect to it directly. So here you can see that I've connected to the Galea network right here. I connect to this, and actually what's really nice about this is you can connect automatically here. So after your first time setup, all you have to do is turn on the headset one time, connect, and you're good to go, and you're ready to stream data in. So we've kind of streamlined our connectivity process. We've also improved some of the tools that we've made available to VR developers in Unity. Now, if you tune into our previous webinar, we talked you through how to go from a completely blank Unity project into a biometric enabled VR project using our OpenBCI Unity SDK. I'm going to assume for the purposes of this demo that you've already included all of those packages, and you've kind of got the project set up following those instructions. And once you've done that, you'll see this prefab folder in the OpenBCI packages folder right here. Now in here, you'll drag in the Galea headset game object or prefab, just like you did last time. But inside here, you'll see a lot more game objects underneath the root game object. And so most notably under this heading called metrics, you'll see all of the things that we just talked about: the time series, the restfulness, the mindfulness, band power, oxygen level, heart rate, and all the facial gestures that we were using in the game that we just demonstrated to you guys. And this is the point in your application where you can subscribe to that data. Like, these are the components that will provide you that information, so you can integrate these into your own VR applications and create new VR applications. And this is everything you need. The other thing we added was bringing in different types of streaming mode. So one of the other pieces of feedback we've received is that it would be really nice if we could just get some data flowing, even if you don't have a headset or you don't have the headset hooked up. Maybe your buddy has it or something like that. And so we've created different streaming modes, one for the physical headset, that's the Galea streaming mode here, and also in synthetic Galea, which will create representative data, but is useful for development purpose, so you can iterate really quickly. The other thing we've done to improve the development process is make our metrics, enable them to be set manually or to work normally and stream and basically classify information based on the data streaming in through the headset. This is kind of useful for applications where you want to test kind of edge cases while you're in your development process. A really nice example here is the oxygen level metric. Now, if you don't want to hold your breath a whole lot, every time you need to check what your application does when your oxygen level hits like 70, for example, then it would be nice if you could just kind of manually set that and check that your application is working correctly. And so to do that, you can enable and disable these game objects, and that'll let you change the values here directly, but from your own scripts, it'll still be able to interact just like it would if it was streaming live data in and giving you a live metric. So these are a couple of the different features that we've added to the SDK to try and improve the quality of the development experience working with Galea. Cool. I think the last thing, go ahead, Joe.
No, I mean, we've got a handful of questions to answer, but if there's one more little piece of things that you wanted to get through, let's knock that out first so we can run through a couple questions.
Cool. The last thing I'd like to talk about today is just showing you guys how this all works through the OpenBCI GUI. Now, this is the GUI that we've shown you in previous webinars, but for those who are new, maybe you haven't seen this yet. So I just wanted to give a chance for you to see the other side of our tool set, which is this visualization system that we have in the OpenBCI GUI. It's nice. You can go in here, visualize your different types of data. If you're interested in like a networked application, you can stream out data from this GUI in a number of different ways. We have UDP protocols, serial protocols, OSC, and LSL. LSL is a really popular one. This supports a number of different applications. And so if you need to stream to those applications, you can use LSL to make it happen.
Yeah, it's actually a question in the chat. There's one that's is it compatible with LSL or Python to be able to integrate additional sensor data? And the answer is yes. You know, we support both. You can get the raw data out into both. And actually, it's through LSL that we were able to do, you know, an integration with iMotions and several other kind of software providers that work with these types of data.
Right.
So, Chris, yeah.
And the Python question is a great question too. So you're able to interface with Galea using the BrainFlow open source project. And the BrainFlow project integrates as bindings for Python, C#, C++, it's written in C++, Rust, MATLAB, Julia, and probably some others that I'm not remembering off the top of my head. It has bindings for support a wide variety of different pieces of software. Cool. Now, you've kind of seen this time series widget over here, and now we're kind of streaming some data, and you can see that coming off of Musa's head here. What you haven't probably seen yet is this signal quality test widget over here, which is giving us an idea of kind of what the health of our different sensors are. In order to get good data, you need to have good contact with the skin. And so this widget will help you check the sensor placements and adjust them as needed to make sure that you have nice signal quality. So here it's going through here. You can see blue generally means good. Red means that it needs that the channel is railed. And so we can try adjusting it. Try adjusting the right side of your headset a little bit.
Yeah, it's not contacting properly.
There we go. That fixed it. So you can see that this one went from red there to blue when we got good contact. And actually right now, this looks pretty good. Now, there are a couple other widgets that you can use here as well. There's an EMG widget. This is kind of similar to the things that we were showing earlier with the facial classifications. Can you maybe do some eyebrow movements and some cheek movements? You can kind of see how each of those different sensors is lighting up here. So in addition to the EMG widget here, we have a number of other useful things. You can look at FFT plots. You can look at your average band powers. This is very similar to what you saw in Unity earlier. So a lot of these things are available here in the GUI as well. One of the really useful features too is you can go into your hardware settings. So I'm going to stop and change some hardware settings. And you can change the gains on some of your different sensors. And this is pretty useful because if you want to say make something a little bit more sensitive or a little less sensitive, you can go in here and change the gain settings on your hardware. Start this back up. Cool. So I think that's pretty much everything we wanted to cover today. Are there any other questions that we can answer, Joe?
Yeah, let's run through a couple. One of them from anonymous attendee. Are you planning any SDK features for ERP analysis, or for working with evoked potentials?
Yeah, that's a good question. And so these are definitely things that we're keeping in mind for future development. We get these requests a lot for different types of ERPs and different tools that we can basically use to make it easier for researchers to get off the ground and get started faster. So definitely something we're looking at for future releases of the SDK tools.
Yeah, I can say, we've actually already built, some for, SSVEP and P300. We've used those internally to test different versions of the hardware and software. Part of the plan is certainly to package those up into starting templates, that come along with, with the software and the other Unity packages that we're releasing as part of the system.
Yeah, absolutely.
So there's a handful of questions kind of about, the longer term pricing and kind of like, how do we get this into a consumer level device? A couple different questions from Marius related to that. I think, like I said, what we've learned from kind of the years of putting this hardware into the world is we've started with the research audience, and that's moved into then business, and then that gets starting to minimize down into consumer level, consumer level applications once the science behind it's been proven. So right now it's definitely, we included every sensor that we could, into a sensible hardware design, and are trying to get that out into the world as kind of the Ferrari of development kits, for people to get started with. I think absolutely the longer term, like once this has been in the world, we think there's an iteration by businesses and by companies that are going to take this and go, what's the smallest set of these sensors that I can minimize down for my specific use case, whether that's gaming or meditation or neurofeedback or even medical research. So for a gaming specific application, yes, I think we may find that all of the EEG sensors aren't necessary, or really I just want to hone in on PPG and EDA as my two modalities, and then sort of a much simpler version with a price tag in the really a BOM cost in the hundreds or dozens of dollars if you're operating at Facebook scale or someone else's. You can get it will get minimized down and brought the cost way down. Our plan longer term for Galea is to learn really put this brand, put this device into the world, learn from the early customers, and then adjust the hardware and potentially spin it out into multiple devices. Spin it out into different devices at different price points based on the use cases that emerge.
Great.
All right. What else do we have? What does the open part of OpenBCI represent? That stands for open source. A lot of the features of Galea will be, there's going to be an open core to Galea, that will be released for people to tinker with, and then some of the features will be part of kind of the premium software package that comes along with it.
Yeah, and you can take off the headset now. Yeah, and also a few more bars on that as well, Joe. I think that really the open part of OpenBCI 2 is related to the open source projects that we support, and you've mentioned this as well. Our GUI, we have a GUI for our projects or our different sensors that we support in other parts of the business. It's open source. You can go in there, you can create new widgets, you can contribute back, and you can fork it and use it however you need to. We support different open source projects. I mentioned BrainFlow before. This is a project that we support. And great open source project, supports a variety of different sensors. And so in everything that we do, including our work with future versions of Galea or whatever comes next, there's going to be an open core to what we do. There might be other features as well, but there'll always be this kind of open source core because it's a core part of what we do here in the business.
Question from Javier. Does the system, and actually this might be good to frame, does the system does it need to build a user profile before using it? Do you need to train it? Do you need to calibrate it? Maybe, Musa, maybe it's easier to answer this, is like, based on everything we showed today, was anything trained, specifically to you or Phil?
No. So I work primarily on all the data science related stuff, so all the machine learning. And I can tell you that we're, at least what we're aspiring to, is so all of our models generalize to a wider population. And even testing internally, where we're training on like dozens of people or less than a dozen people, we want it to generalize well to outside of that. And the advantage to doing this is that when you have a good model at a small scale, the more data you add to it, the better it will get. So if it generalizes well early on, you know that the more you train it later on, it'll improve even further. So we can see even better accuracy and possibly even more features as we go forward.
Great, thank you. All right, just clearing up a couple questions. We got a question from Nam about, are we looking to expand the number of EEG channels? I can answer that, yes. For the beta hardware, we still have an opportunity to add electrode locations to the montage. So specifically, we're trying to incorporate 2 more. Actually, Musa, maybe you can help me out with the 1020 locations that we're looking at.
Yeah, so I discussed this with the hardware team earlier. So we're looking to add more EEG channels, particularly on the current design. I guess I can pull it up. We're missing out on the parietal and temporal area. So you can see there's just a hole directly through it. So we're going to add, in that blank space that you see, we're going to add at least a couple of electrodes so we get more of that like motor cortex information and parietal lobe information.
Great. I guess kind of a more general question overall. Do you have any kind of, like, how can this be applied for neurofeedback or biofeedback applications?
So, I mean, the idea behind this neurotechnology headset is for this exact application for biofeedback. That being said, we haven't done a whole lot of testing in this area just yet, but we have a lot of experience in the past, personally from my PhD work and a lot of other members of the team. Like, we have a lot of history in this area, so we're going to be doing more testing, and you should keep an eye out for that in the future with the Galea.
Yeah, and some of the work we've done internally too has been related to visual feedback and auditory feedback as well. These things are well suited to virtual reality, and that's part of the reason why it works so well with a VR headset. And so it's very easy to do things like visually evoke potentials. We can do biofeedback to help you modulate different like audio frequencies using different brain waves. And so, yes, absolutely, this is something that that you can do with Galea and that we're going to do more of in the future. Oh, I think you're muted, Joe. I can't quite hear you.
Thanks, everyone. Yeah. There's another question actually about where showing the kind of install of the SDK in Unity. I'll make a note of that. We're going to send, we'll send an email out following this that includes the, includes the recording and kind of a follow-up email after this. So we can reference the link back to the previous webinar, the specific, part of the video where we go through that installation step, but it might be worth us just sort of recording a shorter, like, here's how you get started, like video of that rather than having it be a timestamp in another, hour-long video.
Sure. And really briefly, I can talk a little bit to it. Basically, we distribute a tarball. It's a Unity package tarball. For those of you who are Unity developers, Unity package is a little bit of a two-faced term. One can mean you double click on it and it imports a bunch of assets for you. It's not that. It's the NPM related, the Node Package Manager related package. We distribute it as a tarball. You can add it in through the package manager, install it, and it'll install dependencies for you. We also use the Vario eye tracking, and they have a Git URL that you can also add from the package manager. So it's a pretty simple process, but we can definitely send recordings to make it easier for folks to get started quickly. All
right. So I think we got time for one last question. Let's see. The most off the top of the queue is, do you use EEG to classify any movement related task in our demos? Or was that, was EEG being used to do any of the movement related stuff?
For now, we're not using the EEG for anything specific. We are doing like basic metric derivation for mindfulness and restfulness, but beside that, we haven't really got around to using it yet. But I have to say that we are working on something similar to that right now, so should look out for it in the future. Yeah, for the facial movement demonstration that we showed today, those are primarily based on muscle movements, particularly the muscles that are going on right here, and then the eyebrow muscles as well. And those are really loud signals, and so it just makes sense to use them because they're there, they're very easy to detect, and they work really well for these movements and these detections. All right, well, I think that's that brings us to the end of our our scheduled time. There's a couple more questions in the chat that we didn't have time for, but you're always welcome to email them to us if you have more questions about Galea, or propose them as topics for future webinars. We'll share, we're looking for feedback from the people that have taken the time to attend for what to cover in the future. So we will be uploading this to YouTube, our YouTube channel, in a couple days once we've had a chance to process it a little bit. And then we are in the last stages of batch number 3 pre-orders at the moment. So what that means is anyone who orders as part of batch 3 will have an opportunity to reserve time with the alpha prototypes that we have before. You'll be able to use the alpha prototypes for a 2-week period starting next year while we are manufacturing the beta devices and waiting for those to ship. So there's still a chance to get involved in batch number 3 if you're interested. You can always, again, just either go to the galea.co as the website, or email us at galea@openbci.com. And then, if you're at CES, we'll be there in January. Say hello. And thanks a lot for joining, everybody. We will, you'll get an email from us with the recording, and keep an eye on our social media for more updates. All right. Thanks, everybody.